Okay, we'll go ahead and kick this meeting off. I'm Barry Halverson, the co-chair of the Lake Lawrence Lake Management District. We have about 15 members of the Lake Lawrence Lake Management District joining us tonight. I'm not going to read out all their names, although I think I've written most of them down. We have Tim Clark, who likes to go by Clark, from Herrera Inc. You still want that? That's what you want to be called, right, Clark?
Yeah, that's fine.
Okay.
Thank you.
He is our project manager from Herrera Inc., who's given us an update on the Cyanobacteria management plan study that they've been doing for over the last year now. So, Clark, with that, I'd like to go ahead and turn it over to you. Just remind everybody to mute your mics if you can, and just turn them back on when you have a question. Thank you.
Hey, thanks, Barry. I just wanted to check in if you wanted to record this or if you already had started that.
I've started it. Thank you.
Okay, great. Hi, everybody. I am Clark. I'm a limnologist here with Herrera. I'm down in our Portland office, and I coordinate with our Seattle office and other offices to help implement lake management studies and development of plans across all of Western Washington. I've really appreciated getting to know Lake Lawrence and its interesting history and its somewhat troubling present state. So today I want to be going through some elements of the study we've done so far on Lake Lawrence in order to better understand its physical and chemical conditions to help inform development of a lake management plan, which will be the next phase of this. As I go through this presentation, please feel free to ask questions to clarify. I'd like this to be discussion. That said, there's a lot of content to go through, so if I need to, I will push the conversation going forward to make sure we can cover as much as possible. But I don't want us to get to the end and then have questions about the beginning, because the beginning is important for the end. So with that, what I want to do is, this is a brief agenda. I'll have a little bit of a break in the middle as well, but I want to provide a refresher of why we're here, why we're doing this plan. Then I want to talk about the development and findings of our water and phosphorus budgets for the lake. At that point, we'll take a quick break and then have a discussion around management options, preliminary evaluation we've done. Then I want to hear questions and discussion from you, especially around those management options. And I'll be really interested to hear what Barry has found today from his conversation with the SEDOX manufacturers. So we're here today, and we've been working on this project because of cyanobacteria blooms or blue-green algae that occur in Lake Lawrence with ongoing frequency, having these unsightly blooms, scums, but additionally they produce toxins. So they're really a problem. They can cause skin irritation, illness if consumed by people or pets, can reduce recreation, smell, have these thick, unsightly scums, reduce water quality as they die off. They consume oxygen, which can impact other aquatic life. And, they also can reduce property values and reduce tourism, reduce folks who are coming to visit that lake. So it affects both the people who live around the lake and the people who would like to come visit it. A little background on lake eutrophication. Lake eutrophication is the increase of nutrients in the lake, which is typically caused by increased land runoff. It's a bit of a different history for Lake Lawrence, which then causes increased algal growth and then decay. There are natural and cultural sources of nutrients, cultural being anthropogenic. Natural would be more like wetlands or the decay of upland vegetation material that's getting washed in. Whereas cultural is going to be more like fertilizers, septic system, effluent, or things that are accelerated, such as logging, which causes increased amount of sedimentation loss, which has a lot of nutrients bound in those sediments, which then can get washed down into receiving waters. So the process of eutrophication is this increase from low nutrient waters to high nutrient waters. And low nutrient waters are typically very clear, can have higher amounts of, have modest amounts of ecological productivity, depends on the fish. Bass and the like really prefer highly productive waters, and other sports fish. So we want to have some amount of nutrients. If you go up into alpine lakes, they can be pretty bare in terms of the amount of wildlife that's present within them. But then we have too much nutrients, we can have these impacts on ecology and human activities. We look to classify lakes into 4 classes in terms of level of productivity, which we call trophic states. The highest is hypereutrophic, then eutrophic, mesotrophic, and oligotrophic. Oligotrophic meaning poor, nutrient poor. Go ahead, Barry.
One of the things I noticed down there was you said there's no apparent trend. Can you explain that when you get to it?
Yeah, I can do. And I'll provide a little more background here. And so the way that we classify trophic states is looking at 3 different parameters, one being total phosphorus, the other being chlorophyll A, which is the amount of the photosynthetic material that's within all plants, including algae and cyanobacteria. And so we can look at the amount of that, and that tells us a good amount of how much algae is within the lake. And then the third parameter that we use is Secchi depth, which is a black and white disc that we can drop into the water to see the clarity of it. And these are all pretty well correlated, and so we were able to develop these categorizations of lake trophic states based off of these 3 parameters. Based on the data from the past 15 or so years from the Thurston County Environmental Health Department, Lake Lawrence would be classified as eutrophic, having high amounts of chlorophyll, total phosphorus, and low clarity as measured by Secchi depth. There is a lot of noise in it, and as you can see, this plot over time on the x-axis is years, and the y is that trophic state with different bands for the categories of trophic state. And while it does, and I would say kind of looking at it from here, we see that it looks like it's increasing, but the last few years there's kind of a drop off and there's a lot of noise. So we can't find a statistical test that says that there is a increasing trend, but that may be more of we need additional years of data to confirm that, rather than saying there is no trend. So
Okay.
that's part of the statistical question is you assume there's nothing there and you have to prove otherwise. And right now, just because of how noisy the data is from year to year, it's hard to find like a monotonic trend that's increasing year over year.
Okay. We have one question.
Yeah, go ahead. I can't see the name.
Frank, go ahead.
Yeah, it's kind of along those lines, and so I'm looking at the Secchi disc depth, which is the circle with the hole in it, right? Black circle.
Yeah.
Okay, seems to me like there's high correlation between not so much the measurements, but the trend of the measurements between that and the other 2, the chlorophyll and the phosphorus. So, to follow on to Barry's comment there, if we use Secchi disc in our measurements going forward when we do our lake surveys, etc., it would seem to correlate highly with those other 2 measurements. such that we could use Secchi disc as a sort of cheap method of staying up with this.
Yeah, and that's a really astute observation, Frank, and I appreciate you pointing that out. So that is one of the wonderful findings that came out of studies in lakes in the 1950s and 60s, that Secchi depth, this fairly simple, cheap disc dropping into the water, can tell us a lot about a lake and a lake's trophic state. Certainly, there's variations for different types of lakes that maybe have more organic carbon in them, something that's being affected by wetlands, that has different reasons for having poor clarity. But for many of the Western Washington lakes, Secchi depth is a really good tell for the lake trophic state in the summertime. So it's great to have chlorophyll as a measure, because that's really, the most direct measure of what we're looking for, which is how much algae is there. And it's great to see that there is this strong correlation, at least in terms of trends. We do see that Lake Lawrence tends to have higher clarity than we would expect given the amount of chlorophyll present, which is indicative of the types of algae that are present are a bit larger and less colonial. So like the ability to see into water is going to be a factor of the size of particles within it. We can see deeper into water if the things that would be obscuring our vision are a bit larger. So that might be, yeah.
I'm sorry, is there a particular part of the visible spectrum that correlates, like, the human eyes is the human eye spectrum, but is there a particular portion of that spectrum that if we filtered, we could break out phosphorus from chlorophyll or somehow get better definition of the Secchi disc reading?
Yeah, and this is a bit of a side, and so I'll answer this quickly, but I'm going to have to keep moving on. So there's been a lot of recent research looking at using satellite imagery, because we have hundreds of satellites now that are passing overhead, and some of them are owned by governments. They share that information, and they look at multiple light spectra. And so there have been studies to develop algorithms for relating the spectrums of light that those satellites are reading to estimating the chlorophyll content. And certainly that's challenging with resolution. And you can do so at like a smaller scale using drones. There's a lot of challenges within that, because water is also pretty reflective at the surface, and you need still surfaces. But there are like cheaper products that are out there, which are sort of more benchtop in order to try to measure chlorophyll without as much laboratory costs. But there's a lot of noise and a lot of uncertainty with those, and they're getting better. But there's still are no substitution for accredited laboratories. But it is an exciting developing science. I think hopefully one that will get better with machine learning. Maybe that's one way that AI will be helpful rather than a disaster. But moving on here. So just to summarize a bit more of that past pod, this is looking at the big East Basin and the West Basin for Lake Lawrence for the TSI values for each of these. This is mostly just for reference. They are all in that eutrophic state, except for the big basin's 2005 TSI values were a bit lower compared to previous years for total phosphorus. And that is just sort of within the noise. I expect that next year we may see additional a return to higher phosphorus values. Again, they're already high. Also, I want to point out that I don't have the complete data set for summer of 2005. I'm waiting on the July and August and September data from John Haberlin at Thurston County Environmental Health. So it's not a complete data set yet, and that might we especially see higher phosphorus levels later on. So I expect those would bump up. So, and what we're really concerned around in Lake Lawrence and other Western Washington lakes is Cyanobacteria, blue-green algae. It's a primitive algae group with a more bacteria structure, but also has those photosynthetic pigments, has that chlorophyll, which we're able to measure. It has several competitive advantages over other algae. It's able to vertically migrate up and down the water column by regulating their buoyancy. This is why they form those scums. They come up to the surface to be able to outshade their competitors, have greater access to light, but then also go down and collect nutrients from deeper in the water column. And not all cyanobacteria species are able to do this, but some of the ones we're most concerned around are able to. They're also able to have luxury phosphorus uptake, as in they're able to store and have reserves of phosphorus over time. So that when there's an abundant phosphorus in the water, say after a storm, they could take on some of that phosphorus, and then later in the year when it's more competitive, they still have those reserves of phosphorus. They're able to keep pushing on. Grazers, which are like zooplankton, Daphnia, or water fleas, don't really like to eat cyanobacteria. They're filamentous. They don't have great nutritional value. They prefer to eat other types of algae. Some of them are able to fix nitrogen gas, which is nitrogen is another key nutrient for cyanobacteria and all algae. And so the fact that some cyanobacteria are able to create their own gives them a competitive advantage if there are not enough nitrogen ions within the water column. They also are more primitive, and so they have lower energy needs, and so they can grow under lower light conditions as well, sort of deeper in the water where there are more abundant nutrients. So they're really able to thrive, and they can really take advantage of situations where there is excess phosphorus. This is a plot here of the amount of days, and so in addition to that, cyanobacteria can create cyanotoxins, microcystin, which is a liver toxin, and anatoxin, which is a neurotoxin, which are can be quite harmful to human and animals. So in the plot here, there are 4 cyanotoxins shown here. We're predominantly going to be interested with anatoxin in the upper left and microcystin in the bottom left. Cylindrospermopsin and saxitoxin are not as typically found in Western Washington, and so they're just not measured. As the y-axis here on the left-hand side is showing the number of samples that have been submitted to the King County Environmental Lab by year, with the red bars indicating those that exceeded state recreational guidelines. When those guidelines are exceeded, Thurston County Environmental Health may decide to close the lake, putting or at least issuing a warning or danger for the lake. On the right, I have the number of days in which the lake had a posting for warning or danger. This is coming from the records from the Lake Lawrence Management District. These are very helpful to be logging when the lake is closed and open or has these warnings present. Not every lake district or every health district tracks this information, and it leads to some challenges in telling the story around why this is such an issue. But as you can see, there are many days. Sometimes it's 2 weeks. 2024, there was 147 days of warning or danger on the lake, including sort of drifting into February 2025. So that 2024 includes the fact that those blooms continued through 2025. Whereas the 28 days I'm showing in 2025 is just for this year alone. And I'm hopeful that there are not new blooms that will arise to close the lake, but I think there may be some, Barry.
Yeah.
Did I see that in the news recently?
Yeah, we notified county about a bloom yesterday. They can't get out to do any testing till Monday.
Okay. to them about, I guess, King County Environmental Lab wants the samples to come directly from the health departments now,
That's
rather
correct.
than individual.
Yeah,
Okay.
I've talked to them about taking the samples and sending them, and they said no.
I have opinions around that, but that's
Yeah.
not the purpose of this conversation.
Right.
So this is an issue, an ongoing issue. Since the program started with Northwest Toxic Algae, we've seen high levels of cyanotoxins in Lake Lawrence. So that is why you as a community came together to get a grant from the Department of Ecology to develop a lake cyanobacteria management plan. The purpose of this plan is to develop near and long-term actions to manage water quality in line with goals and objectives, which is really to decrease the frequency and duration of these cyanobacteria blooms in order to extend the enjoyment of the lake. At the end of this project, we will be delivering to you a lake cyanobacteria plan for Lake Lawrence. This is an outline of that plan. We'll have background information talking about the history of the lake and its watershed, what actions are currently being done, what are the current conditions, identifying goals, summarizing the findings of this monitoring study we've done over the past year and a half, a summary of the water and phosphorus budgets, which I will be going through today, and then a recommended management actions and the sequencing of those and what are the costs of those. So what we want to do is develop a plan that is implementable. I've been around long enough, and it's not that long, but I've seen enough plans be made and then put on the shelf because they are not feasible to implement. And so what is really critical, and what I'm looking forward to at the end of this meeting is have a discussion about what are the pathways forward that the Lake Lawrence community wants to implement and have community support, and then identifying funding structures in order to implement them such that it can be done, such that we can improve the water quality of Lake Lawrence. Additionally, we'll have a framework for adaptive management, for looking to examine how the implemented actions are being effective or not, and making adjustments as needed. And then we'll have a bunch of appendices with raw data to your heart's content. And I think it's important to iterate that this plan focuses on surface water quality. We're not going to be looking to manage fisheries, aquatic plants, drinking or groundwater quality, flooding. Certainly, we're going to consider co-benefits and consequences of management strategies on those endpoints, but they're not the endpoint that we're looking to optimize for. But that's part of this discussion we're going to be having today and through the end of this project. So we're developing this plan to make sure that the strategies that we're developing aren't going to be negatively impacting other endpoints that we care about. So in terms of the schedule of this project, we're here today. We've completed all lake and watershed monitoring. We're awaiting some of the final data analysis from the laboratories and going through QC processes. But today we're talking about the phosphorus budget results and identifying potential management actions. In March of next year, we'll have a early draft plan that will be available for the county and the LMD steering committee review. Following their comments, we will have a public meeting, as we are right now, to present that draft plan after taking in the county and steering committee comments. Then we'll take that and draft plan and give it to the larger community as well as the Department of Ecology for their review. And then in June, we'll present that final plan, any updates since the draft, and deliver it I really like to use that final meeting to start game planning for the next steps, for identifying funding structures or potential partners. For example, recently worked on a project up in Skagit County on Lake Campbell, and it was during that meeting in which we identified reaching out to Washington State Department of Transportation because they were working on a roundabout nearby, and we had identified that drainage area that a roundabout was in as a high source of phosphorus that was coming to the lake, and we reached out to them to say, would it be possible to put in stormwater treatment here that was optimized for phosphorus removal? And so that process is great because that's something they were already moving forward with, but now it was an added consideration, and we're able to talk with them early on in the planning process. And so this is the time when we want to be looking and to expand for collaborators, and we'll be inviting Department of Ecology, Joey Terracy, to that meeting as well. And I know that and Barry and other folks on the steer committee, I want to work with you to identify other collaborators who would like to invite, but we can talk about that later. So I want to talk a little bit about the goal of this project. We want to develop a comprehensive science-based plan to guide public and private investments for the benefit of human recreation and environmental health within Lake Lawrence. Within the water quality monitoring goal specific, we want to understand what are the current water quality conditions and plankton dynamics within Lake Lawrence, and then also compare water and phosphorus budgets since 1990 when KCM conducted a study. I really wanted to see changes within sediment release, because that's a big piece of the puzzle here is where is the phosphorus coming from? This water quality monitoring study included several monitoring sites for water quality and sediment quality. The blue triangles here indicate where we measured lake sediment or lake water quality, as well as taking sediment quality samples, took cores, which I'll talk about more later. And then there's two additional sites where we took additional sediment cores to look at variation of phosphorus in the sediment. Additionally, we looked to measure flows coming into and out of Lake Lawrence. This was a challenge over last year, and I'll talk more on that, but we looked at three drainages that come into Lake Lawrence, as well as looking at the old ditch of the diversion from the Deschutes River and looking at the outlet. And then also the observations of lake surface level at the two existing gauges, which have been very helpful. And I want to acknowledge the folks that went out over the past month or so for increased lake level logging, as we were seeing an increase in lake levels, and I was looking to explore some questions I had around the relationship between groundwater levels and the lake level. So I really appreciate that. That has been, those data sets for the lake level have been really critical in the development of this water budget and phosphorus budget. So I've been throwing these around a bit, lake and water phosphorus budget, but what are those? Let me talk through that really quick. So a lake budget is dealing with tidying up and accounting for what goes into the lake and what goes out of the lake. And for whether it's water or phosphorus. So a primary source of water to Lake Lawrence is precipitation itself, what's falling directly onto the lake. Additionally, there's water that's falling elsewhere in the watershed, and if it doesn't infiltrate and runs off, it stays on the surface. We want to account for that, and we call that runoff. Those that that water that infiltrates and slowly moves into the lake is groundwater, that's subsurface flow, and we look to account for that as groundwater input. Additionally, there can be groundwater that's leaving the lake depending on the height of the groundwater, the water table around the lake. So water can be moving in or out of the lake subsurface depending on the level. Additionally, there's going to be water that leaves the lake through the outlet. During our study period, there wasn't too much water that left through the surface or that outlet just because it was lower throughout the spring. But that's a critical piece of the water budget. Additionally, there's evaporation from the lake surface, which is missing here. I think this is mostly a thing about phosphorus, which I'll talk about in a second, but we also want to account for the evaporation off the lake. In the same way of the water budget, the phosphorus budget is looking to see how much phosphorus is coming into the lake, is staying in the lake, is leaving the lake through that outlet or through groundwater, or is falling, because that phosphorus is frequently bound to algae or other particles, and so that will slowly settle down to the lake bottom. So again, there's going to be some amount of phosphorus that's in particulate matter, that's the atmosphere, and precipitation is going to provide loading of phosphorus. There's phosphorus on the landscape, which can drain in through runoff. Phosphorus is present in groundwater and nutrient-rich soils, and furthermore, that is made richer in phosphorus, enriched by septic system effluent. Septic systems are really great at providing some level of treatment for wastewater, but for phosphorus, they're not so great. They really rely on the surrounding soils to attenuate and capture that phosphorus. But in well-draining soils, that phosphorus is not easily captured and can contaminate the groundwater. There's a lot, we contain a lot of nutrients. Additionally, as sources of phosphorus to the lake are birds, from birds overhead, just flying overhead. There's some lakes that are really impacted by gulls, as well as waterfowl. Those are more resident that can eat algae or plants in the lake and transform that and then defecate into the lake, and that's a source of phosphorus in that transformation. Aquatic plants are another source. They can take up nutrients from the sediments as well as from the surrounding water, store that phosphorus in their tissue, and then when they decay, they release it. As I spoke to, that a lot of that phosphorus also falls down to the bottom of the lake, and Lake Lawrence has an interesting history in which the Deschutes River was diverted, and there's a huge amount of sediments that were brought in by the Deschutes River during that diversion period, and those were actually quite rich in phosphorus. And so the sediments of Lake Lawrence are rich in phosphorus, and they continue to have more phosphorus dropped in them as that algae is growing and dropping down. Certain chemical and environmental conditions allow that phosphorus to be released from the sediments, and that can be mixed upward, or those algae that are able to vertically migrate or enjoy or able to survive in low light conditions are able to take it up, and then that phosphorus is able to come up into the water column and be used. That's that Cyanobacteria migration here. So these are all the elements we're looking to account for within our water and phosphorus budgets. So another way of looking at it, if you're not a diagram person and you're a table person, here's a table. And this is what we're looking to capture within our budget. So we have the change in storage, which I didn't explicitly say, but we also wanted to track, that's a big part of looking at those lake levels, is seeing how much water is just staying in the lake and not leaving, just sort of building up over time or going down. And so that's something we think about for both water and phosphorus. Direct precipitation for what falls on the lake surface, we include that in both these budgets. Evaporation is only taking away water, it doesn't take away phosphorus. Surface runoff is in both of these budgets. Lake outflow is in both of these budgets. Groundwater going into and out of the lake is in both of these budgets. And then internal loading, that release of phosphorus from the sediments or the transformation from aquatic plants. I also include waterfowl here, because it's sort of happening within the lake itself, not coming from an external source, as well as stocked fish, because DFW comes and stocks fish with rainbow trout catchable, and those have a amount of phosphorus that they contain. A lot of those are removed through fishing, but those that remain still have a measurable amount of phosphorus that are contributing to the lake. So now I'm going to walk through each of these sources and talk about how we collected data and what we found. First, starting with change and storage. On the left here is a plot of the level of Lake Lawrence. This is a combination of both gauges. The red line indicates the water year 2025. A water year is October through September. So water year 2025 is October 2024 through September 2025. The gray lines behind it are past water years. And so some things I really want to note here is that we really didn't have very high levels of water in the lake in the wintertime. In fact, it really stayed pretty stagnant from January through March, and then it started to increase. And the outlet of Lake Lawrence is regulated by its level. So up until we hit that crest, maybe a little bit below it, where we can seep through the cracks, we're not getting outflow from the lake. And this is different than past years, where we can get up and above that outlet, which is about here. So we can see that in past years, there was often more outflow more consistently from the lake. It was also at a higher level. Ending the year, it's a little bit below average, but I know that right now I'm interested to see the latest updates to the NASA website for the Lake Observation Network for the level of the lake, because I imagine it's quite high after this atmospheric river has come by. So looking forward to surpassing this very dry year, or this past dry winter. Looking at that level, we're able to look at the changes in lake volume in terms of thousands of cubic meters, which I'm showing here on the y-axis, as long and grouped by year. So in October, there was a little bit of loss of the lake volume. In November, there was an increase by about 600,000 or 60,000 cubic meters, much more in December, January, not as much, and then sort of increased through March. And then once we got into April through September, we had a steady decline in the amount of volume, the amount of water in the lake itself. These are all negative numbers indicating that there's a loss of the amount of water in the lake. Similarly, we can look to see how much phosphorus was in the lake just within the water column. This total phosphorus is inclusive of dissolved phosphorus, free ions, and particulate phosphorus, which would be phosphorus within algae or other sediments, or even in water fleas. Typically, we don't get a fish when we're capturing it, but if we were to, we would measure that as well. So on the left here, the plot is the concentration of phosphorus over that same water year. period. Again, we're still awaiting final results for July, August. So I'm using assumed values from past years of the concentration of phosphorus for this water budget. So this is still preliminary, but as that data comes in, I'll be able to complete it. But I expect conditions to be fairly similar to years past, looking at averages. So really, if we look at the concentration over time, typically the concentration of phosphorus is pretty stable throughout the winter. And then once we get into the spring, the deep waters of the lake, or the hypolimnion, which is the bottom layer of the lake, starts to have higher and higher increases of phosphorus. And this is indicative of that sediment release. And then that surface level tends to increase as well as you have more and more algae present. And we see that uptick later in the year. The blue line here is a weighted value of that. So thinking about how much volume is at the surface and how much volume is at the bottom to create a weighted average of that. And that's what is used in order to determine the amount of total phosphorus within the lake over time. And that's shown here as these sort of significant losses and then significant gains in the amount of phosphorus we're seeing in the lake itself. Barry, you have a question?
Yeah, I was just going to ask if you've contacted John, and is the county receptive to getting you that information?
We have contacted John with a good frequency, and we are, I think they have been wrapping up their sampling season, and so they've been delayed because in addition to being the data manager, he's also the lead field staff, and so has been, I guess, underwater, or over water, but he has said that he will be getting it to us very soon.
Okay.
And as long as we have it by the end of the year, I already have all these mathematical models set up, so all I need is that new data to sit in. So it won't take too long on my side.
Okay.
But certainly, the sooner the better.
Okay. Well, I'll send you what he just sent me, just in case you didn't get it.
Okay. He didn't send it to me.
Okay.
I'm a little jealous now. Okay. Moving on, the next source of water and phosphorus I want to talk about is precipitation. Similar to that graph I showed around lake level, we're looking at precipitation over the water year, with a red line being the 2025 water year. This is the total amount of cumulative precipitation over that year. So we're starting at 0, and then as it rains, we're increasing this line for the amount of rain that's fallen. So at the end of 2025 water year, it was about 32 inches fell, which is at the lower low edge of norm for Lake Lawrence in this area, but not the lowest it's been. And we can see that same stagnation in January through March here, and as well as that not too much rain in April and May. Janice?
Yeah, I was going to ask, on the previous slide, there was an increase in May, a decrease in June, an increase in July, a decrease in August. I was assuming maybe that had something to do with the water budget fluctuating, but the slide you were just on shows that the precipitation was pretty flat.
Yeah.
So I'm not understanding why the phosphorus levels flip-flop like that.
So the phosphorus levels flip-flop for several reasons. One, there's a lot of noise inherent to sampling the deep waters, and so this is really matching these concentrations we're seeing here. This peak is probably associated with this peak, and then we had this lower concentration that was measured, and then a higher concentration. And sampling, so what we're doing is dropping a canister, essentially. It's called a Van Dorn sampler, and it goes to about 6 meters depth at Lake Lawrence, and then send a messenger down, which is a weight, and then that closes it, and we can bring that up. So we're really, we're collecting about 1 to 3 liters of water at a time in order to characterize the entire lake. And so there's going to be a lot of noise within that. And so that's why we want to collect multiple samples over the year to look at this. And so this is going to sort of average out as we're looking at this within the water column. But really what's happening is that sediment release that's happening is not continuous. There are going to be shifts in that. There's different levels of algae at different times. So there's, in addition to the variability of when you take the sample and just where it is within the lake, there's also variability over time of the content and the other biological processes within the lake.
So we don't necessarily, there's noise, and it depends on where the phosphorus is located in the water column, and so that can affect your results. Do we know why the sediment would be releasing more phosphorus at a particular month than another?
With this data set, no. That would be difficult to determine. There can be several reasons. Sometimes it can be due to wind force mixing or like temporary oxidization of the lake, where like the surface, where the thermocline breaks. The thermocline is that density barrier of warmer water at the surface and colder water below. That can break down and cause some mixing to occur, which if there's increased oxygen at depth, and I'll talk a little bit more about this later, then that sediment release rate will decrease. Additionally, we're thinking about other sources as well here. So in May may be a time where we're seeing increased amounts of groundwater input that are coming into the lake. And then as the groundwater table goes down, we can have more export of it. So it's capturing a lot of things here is storage. And so as we look at these different sources, this is helping us to puzzle it out. So I'm going to keep moving on to make sure we can get through these budgets and take a break, and then we can come back to start talking about management options. So with precipitation, we want to look at this as well. These bar charts are representing the amount of volume that's falling directly on the lake. This is as simple as looking at the depth of rain and multiplying it by the lake surface in order to get the volume that's coming in. And then there have been studies that have looked at the concentration of phosphorus within rain, which is about 24 micrograms per liter. So we can use that depth of rain multiplied by that concentration to get the load of phosphorus that's coming in through precipitation. Evaporation is what is leaving the lake surface. There's a nearby Washington State University Agricultural Weather Network station that is able to provide estimates of evaporation potential, and we're able to use that and apply it to Lake Lawrence to look at how much water is going to be leaving the lake. And this isn't a source of or departure way of phosphorus, so I'm not going to show a green plot here, but this is how much is leaving the lake through evaporation for water. We looked and tried to characterize surface runoff into the lake. This is a photo, I think, probably taken by Barry or our field staff, David Garcia, of at the Lake Lawrence Community Center. We had goals of collecting 4 storms over the course of the study period, but due to how well infiltrating the soils around Lake Lawrence are, there were a lot of false starts, and really have a lot of thanks to Barry for being our eyes down there, for letting us know not to come down, that there is no flowing water at any of these surface locations that we identified. We had to make a tough decision earlier this fall that we're not going to continue targeting these samplings, because we had to shift into the analysis component of it, but Barry sent me some photos yesterday, and I saw that flow, and I'm kicking myself a little bit for stopping, but I think it's okay. As you'll see soon, the surface runoff, because it's so well infiltrating, really is not that significant of a source for either water or phosphorus to the lake. It's really going to be that subsurface that is where most of that water is going. Showing the results here from those two events, looking at the three sites that were runoff. We also sampled the ditch on the southeast side. It had much lower concentrations, and so we expect that to be more similar to what is in the lake. You can see that these are in the hundreds or so, whereas the ditch is in the tens. Our average that we found is 160 micrograms per liter, putting together all of these. In the 1991 study by KCM, they had determined a value of 192 micrograms per liter. So our 160 is really close to that 192 for developing a phosphorus model for what's coming in through surface runoff. To estimate flows, we used a model for how much we expect to be going into the lake. That model is based off of the what's on the land surface and areas that are close enough to drain to the lake. And so that's really looking at what we call the runoff coefficient. The lower runoff coefficient is associated with impervious areas, places that don't have concrete, that have well-draining soils, whereas parking lots, roadways, roofs have higher runoff coefficients. More of that water, when it rains, is going to stay on the surface and run off. And if they have a pathway into the lake, they will go into the lake. So we use this in order to estimate flows. Again, we're bringing precipitation here to determine how much is falling on the land surface, and then these runoff coefficients to determine how much is reaching the lake via surface runoff. And so this, if you were to put this side by side with precipitation, it's going to follow the same pattern. And so these are estimates in thousands of cubic meters for the amount of runoff that's hitting the lake. And then mirroring that, looking at that 160 micrograms per liter of phosphorus, we can estimate how much phosphorus is coming in from that surface runoff. Then we also want to look at what's leaving the lake. This is most important for our water budget and phosphorus budget. During the days we went out there, February, it was dry. There was no water leaving the lake. And then in our April event, we saw the level just at the height of the weir, and so we were getting some outflow and able to measure that. I really love this shot. I think it's gorgeous. I love a rainy day. So this is that shot of lake level as it relates to the height of the weir. And what we see is that there's really just that really short period of time in which the lake level was above the weir, in which we would exceed outflow. Using past years and model information and our measured flow at that time, I was able to relate lake level to the amount of discharge, the flow of water out of the lake, to estimate how much flow in cubic feet per second was leaving at a given time. And so we really have this small peak in April of 2025 for water leaving the lake, and therefore phosphorus leaving the lake. We estimate this based off the surface concentration of phosphorus in the West Basin, because that's going to be what's leaving the lake at the surface. For groundwater and subsurface flows, these are really challenging to physically measure. They require drilling of wells in order to determine what is the lake the water table surface, and then requires modeling and a lot of assumptions in order to determine flow in and the direction of it, and it's highly variable around a lake. There can be an area where the groundwater is higher than the lake, and another area where it's lower. And so our approach for these projects, due to the limited budget, is to determine the amount of groundwater flow coming into the lake as a residual in the water budget, as in looking in the difference of how much has gone into the lake, how much has the lake gone up or gone down, and how much is leaving the lake. And the difference between those tells us, well, this must be groundwater, because that's the only source we haven't accounted for. What I'm showing here on the left is an example of when water would be flowing to the lake, where we have a water table above the lake. And then on the right is when the water table is beneath the lake, and so we'd have water flows coming out of the lake. Showing the way that we calculated this residual for estimating groundwater flows here. So we looked at each month, looked at the amount of inflow for precipitation and surface runoff, the amount of outflow, evaporation, and surface outflow at the lake outlet, and then changes in lake volume to determine that residual. When we have a positive residual, that's indicative of more flow coming into the lake from groundwater, because we didn't account for it otherwise. And when it's negative, that their water table around the lake is lower, and we expect water to be leaving the lake. I see there's a couple questions, so go ahead, Frank.
Yeah, can you hear me okay?
Yeah.
Okay, sorry. We know our lake is spring fed. Is that included in the rough terminology of groundwater flow?
Yes, that would be included here.
Okay, because that is seemingly, I don't know the geology of the lake, but it's seemingly, I use a term like a water tunnel that can't come from somewhere else, not near the lake. In other words, the water that comes up through the spring, that the aquifer that provides that water, I personally, I don't know, Barry, if you know, or John, or guys been around for a while, where that source of spring water comes from.
No idea.
There's conjecture in the past that comes from our nearby hills. So they're putting, pressure, hydraulic pressure that causes that spring water to go underground in the mountains and then show itself up under the lake or into the lake. I don't know that. I don't know if the county knows that information, if they have a map of the aquifers. Anyway, the point I'm trying to make is that the source of that water is seemingly important, because it may be different than the groundwater that you describe here.
Right, and whether it is water that is infiltrated nearby or water that is coming through a spring, this residual method would be accounting for it either way. Because really what we're looking for is the difference, what is not accounted for from our measured inflows and outflows. So through this methodology, this would be able to capture both a spring, a channelized spring that's coming in the lake, as well as the more diffuse areas around the lake. But certainly identifying that, and if there are concerns around contamination, that would be helpful. And we can look into that. I've had some conversation with Kevin Hansen, who is the hydrogeologist with Thurston County, and he's provided some information, but for the most part, his efforts have been focused on the Tri-Lake area due to concerns for drinking water contamination there. And so there's less information and less effort has been put in around Lake Lawrence. And I think that would be interesting to find out. But for the purposes of developing this water budget and phosphorus budget, the source is not needed at this time, based off of findings overall.
I guess my point is, if we knew what the source of that was, or we knew the spring water was, let's say, more contaminated than what comes in through this groundwater, then the source would be the spring. I'm being facetious here. So the spring's contaminated. Where is that source for the spring water? And that might be so we would, in the big scheme of things, that's what we would go after instead of just generically the groundwater.
Yeah. Frank, I've talked to Kevin, and he is going to come to our annual meeting next year and to provide us a presentation on the hydrology of Lake Lawrence.
Oh, that'd be really interesting. Okay, I don't want to bog down the meeting.
No, thank you. I wish I had all the time in the world.
You've got another question there.
Oh, you do? Let's see, Frank.
I thought Kim had her hand up, but maybe she took it down.
I had my hand up, but I took it down because that's the question I had that Frank brought up.
Okay.
And that was my question as well.
Okay, cool.
Yeah, I think the effort in order to identify that spring and identify its sources would be well beyond the scope of this type of study. I think if Kevin is really interested in that, that's going to be the person to work with and champion. And so I think we can certainly identify that as recommendations for further information down the line. So I've made note of this. Moving along in this, we were able to estimate the phosphorus coming into the lake based off of literature values for groundwater phosphorus concentrations regionally at 63 micrograms per liter. This is what KCM measured locally. And then outflow from the lake is determined by the concentration of phosphorus within the lake itself, because that's the water that's leaving. So this is all can be put together to develop this water budget for Lake Lawrence. What we were able to determine is that the primary source in 2025, so this is only for 2025, was precipitation, making up 1 million meters cubed of water that was going into the lake. Surface runoff was a small fraction, and then groundwater was twice that. That said, in other years, when we have higher amounts of water in the winter and spring, that water table is a lot higher. And so I don't have it presented here, but I did look at water year 2024, which had a higher amount of rainfall. And so that allowed that increased groundwater by about 4 times more. Even though it was just 4 inches more in rain, we had a lot more of that groundwater coming in because the water table was higher. So that water, as it was moving subsurface, is going into the lake rather than around it or beneath it. And then in terms of what's leaving the lake, was predominantly through evaporation. Very small amount through that outflow because we didn't reach that height. And then amount of groundwater out again because it had that lower water table, and so there was more water leaving the lake through subsurface flows. Now moving into internal loading for the lake, and I'm going to try to quicken my step here to try to get through the rest of this for the phosphorus budget, so we can talk about management options after a quick break. So internal loading is looking at nutrient release that's happening within the lake itself. One of the ones that we're most interested in is release from the sediments. As I spoke to in August or September of 2024, we went out and collected these sediment cores from 4 locations in Lake Lawrence, and then measured and took fractions of this sediment core at different depths, the density and feel and smell of this phosphorus, of this sediments change with depth, from really watery and often sulfuric smelling at the surface to more gelatinous as we move further down and becomes more and more consolidated. And we're able to send these subsamples to the lab to measure phosphorus and its different fractions. And so this is some of the information we've got from it for the 4 cores we collected. I'm not going to go through all this information because I already said I'm trying to speed through it, but what we're really interested in here is the amount of iron-bound phosphorus. This is phosphorus that can be re-released under low oxygen conditions at depth. The biogenic phosphorus, which is phosphorus that's related to recent biological activities, so algae and some like plant detritus. This is stuff that will break down and can release phosphorus as it's decaying. And then the total amount of phosphorus that's present in the lake. One of the things we're also interested in is the iron to phosphorus ratio for determining if the amount of iron that's in the sediment right now is able to regulate phosphorus, at least is able to bind to the phosphorus when it does fall down. The general rule of thumb is that we need iron to phosphorus ratios greater than 15 in order for phosphorus to be well sequestered by iron under oxygenated conditions when we have oxygen in the water or in the sediments. However, when there's no oxygen, it doesn't really matter because that iron is going to be reduced and not able to bind to phosphorus in the same way. But what we see in Lake Lawrence is that the iron to phosphorus ratios are pretty variable. In the deepest part, it's around 10, which allows some amount of management of phosphorus through iron near the surface. But at the other location, one of the other locations in the East Basin had a lower ratio. The other one had a really high amount right at the surface. So there's just a higher amount of phosphorus relative to, or higher iron relative to phosphorus here, but the West Basin had much higher levels of phosphorus consistently through the water column. Frank, I hear you got a question, but I want to get through this and we can talk at the break for it. Thank you. So in addition to the sediments, so we're able to use these phosphorus concentrations in order to estimate how much phosphorus is being released from the lake, or how much phosphorus is being released from the lake sediments. We also want to acknowledge those other internal phosphorus sources I talked about, from fish stocking, waterfowl feces, and the transformation of phosphorus in the sediments to plant material by aquatic vegetation. So internal loading has several different ways of trying to estimate. So we looked at sediment release rates based off of literature equations and phosphorus concentrations in that sediment. We looked at the residual in the phosphorus budget, similar to how we did for the water budget, as well as looking at modeled amounts based off of knowledge of how much phosphorus we expect to settle in the lake versus how much is coming in to it, in order to look for what's not accounted for. And so each of these methods allows us to get an approximation of internal loading from the lake, within the lake. But as you can see, there's a lot of variation in these estimates. So for the sediment release rates, using 2 different type of equations, we got between 131 and 241 kilograms of phosphorus being released, which is a substantial amount of variation. Notably, using the sediment release rates is not going to account for waterfall, stock trout, or macrophyte or aquatic plant translocation. The residual would account for that, those other sources, and we estimated 328 kilograms through this, and then through modeling, which which would include all sources, all uncounted sources of loading using methods outlined in Nuremberg 1998, we get an estimate of 163. So what we're seeing is ranges between 131 and 163 kilograms. So what I'm presenting here is based off that internal loading here is 328 kilograms that's associated with the phosphorus budget, but I'm including sediment release here as a component of it. I've been able to account for fish stocking based off of DFW fish stocking rates and have estimated about 10 kilograms of phosphorus associated with the stocking of trout into Lake Lawrence. We have been, and this is something I want to talk to you all about, we wanted to have counts of waterfowl in the lake associated with each of the lake sampling events. We have not received that information, and so we're looking to have to talk to you all about your observations and counts of birds. I know that Barry, you've sent me some emails talk about counts of geese that you've seen on the lake at different times, and ducks. So I would like to have some more of those observations in order to create bounds of estimates for how much loading is with waterfowl. To help provide some context for this, 200 geese, if they were present year-round, would be expected to contribute about 22 kilograms. 200 ducks, if present year-round, be about 11 kilograms, so about half the amount. And that's if they're present year-round, not traveling between lakes or not migratory.
Right.
So maybe we can talk about that a little bit soon. But right now, those are question marks. Some other takeaways here is that we're really seeing that internal loading is a primary source of phosphorus to the lake compared to precipitation, surface runoff, and groundwater loading. And that is going to be comprised of that sediment release, estimated to be about 186 kilograms, but there's a lot of uncertainty around this. Waterfowl, probably in the order of dozens of kilograms, and macrophytes, maybe 50 to 100 kilograms would be estimated. But I would need more information for that, just because we don't have great mapping of it, nor do we have we might have mapping of it, we don't have the density of those plants in terms of enough information to create a phosphorus budget out of that. But macrophytes can be an important source of phosphorus.
Our lake surveys would probably give you that information, because we also counted geese during each of our lake surveys each month.
Okay, great. Yeah, if they're not already on your website, if you can get those to me, I can look to get those incorporated into our estimates here.
Yeah, they're all on our website right now.
Great. Okay, I'll grab those. So then we look at what's leaving the lake. In 2025, very little left through the surface. 20 kilograms left through the groundwater flow in our estimates. The total amount of storage in the lake we expect to increase by about 36 kilograms, but most of the phosphorus that comes into the lake stays in the lake and falls down to those sediments. Some of that is going to be bound and sequestered forever, but a lot of that can be re-released in the future. And so that 316 kilograms is going to be supportive of the sediment release in the future. So this is just my summary here of the water year 2025 budgets, showing percentages as well. And these percentages, water budget here and phosphorus budget here, the percentages are for inflow or outflow, which are these rows broken up here. And then you also have the total change in storage below. So with that, I want to take a quick break. I'm going to drink water, but I know Frank, you had a question, and there might be some other questions. And then after that, we want to talk about the management methods.
I'm sorry, I went offline for a second by mistake. My question back a couple slides was where you had the core sample showed, it looked like piles of poop.
Yeah.
You used the term surface to some amount of depth. Is that the surface, meaning the surface of the water, or the top of the sediment?
Yeah, that's the top of the sediment. Thank you.
Top
That's
of the
a good
sediment.
question. Yeah. So we
Okay.
drop down these tubes to the surface of the sediment, and then we have a weight, and then we kind of just hammer them in
Okay.
until we get there. So this is probably from about 7 meters deep, and then we take about 2 feet or so, sometimes 3 feet of depth.
Yep. That's what we're seeing. I live kind of where it looks like that picture was taken, and I mean the sediment loading on that western shoreline is just really deep. I mean, you can stand there and sink as you're standing there. Your legs continue to sink down for quite a bit into the muck.
And you're just in the western basin, right?
Yeah, it's
Yeah.
where we take it's where we take the Law 2 surface.
Yeah.
That's
Okay.
where we live. Okay. I just wanted to make sure I was understanding the term surface.
Mm-hmm. Yeah, so this is at the deepest part of that western basin.
Okay.
But it's good to hear that this is similar to what you're seeing. Okay. I think we're a bit behind, but I think this is okay. I'm going to go ahead and get started talking about management methods. So to control cyanobacteria in Lake Lawrence, we need to control the phosphorus that is fueling their growth. And the development of our management plan, we want to really lead with long-term management, scientifically sound and proven technologies in our region, what can be cost-effective over a 20-year timeline, not something that requires ongoing costly maintenance year after year. We have a preference for what's going to be ecologically neutral or beneficial. Want to consider phosphorus source control. But also there is sometimes a need for near-term management for dealing with blooms when they happen. Again, wanting to use scientifically sound technologies, something that can help us provide relief from blooms in a few years as these long-term strategies are being developed. Again, cost effectiveness is important. At this time, we might be more open to chemical-based methods, but with a preference for those that would minimize environmental impact. This is thinking specifically around algicides. That's something that is on the table for managing a bloom when it happens. Again, these can be pretty challenging for lake-wide blooms that have been seen on Lake Lawrence. So some of these are the management strategies that we've reviewed so far. Some of these are recommended. Some of these could be feasible as ways of decreasing the amount of cyanobacteria blooms or the phosphorus that fuels them. And then we show them on the left, and some of them we don't have a lot of confidence on them being effective or cost effective. So some of the feasible strategies are hypolymphatic oxygenation, phosphorus activation, which is to inactivate and sequester that phosphorus that's in the sediments at the bottom of the lake using chemicals, alum or lanthanum, which is a rare earth metal, or iron or calcium. Algicides are effective short-term method, but again, short-term and really challenging at a lake scale. dredging was something that was really of interest to the community. Typically, we steer clear of this because it is very costly, but we heard there was a lot of interest in this, and so we've developed methods for that. This certainly could be effective at reducing the amount of phosphorus in those sediments because you're removing all those sediments. And as we saw in our lake budget, phosphorus budget, there's not a lot of external sources of phosphorus, and so that those sediments would not be replenished very quickly. That said, I'll be showing you the numbers from our estimates, and I'll be interested to hear your response from that. Then there's a large host of more experimental or methods that we just don't have a lot of confidence on that would work. I'm still going to talk through those quickly here. So I kind of want to talk through this for an effective method that we've recommended for several lakes, and this is something that Spanaway Lake is implementing now, is to look at hypolimnetic oxygenation. I didn't speak to this too much, but a method of trying to capture and keep that phosphorus that's bound to iron in the sediments is to keep the deep waters oxygenated. And because when those waters lose oxygen, become agnoxic, that iron is reduced and is no longer able to bind to phosphorus. So there are technologies out there like space cones and the oxygen saturation technology that are able to pump oxygen in to the lake. Some of these are hyperoxygenated waters being pumped into the lake, or sometimes just tubes of oxygen itself are pumped down to the bottom of the lake, and then diffusion is allowed to occur, and that oxygenated water is able to move through the sediments and that overlying water such that iron remains oxidized and is able to bind to phosphorus. In some cases, and we saw that not all locations in Lake Lawrence have a high iron content, iron can be added to the lake in order to provide that binding opportunity. Additionally, by oxygenating the deep waters of the lake, this provides added benefit by providing cool water habitat for trout and other cold water fish that prefer colder waters. But right now, because there's no oxygen down there, they don't really go into those deeper waters. I don't think 2026 is the right year, but this would take probably 3 years or so if we were to design, permit, and do construction. So that would be operational by 2029. I think I turned upside down a little bit here, but these are not, they have a high upfront cost for the purchase, as well as permitting and design of this equipment, estimated around $1.8 million. And then the generation of oxygen at the shoreline requires energy in addition to the pumping down. And so it's about $20,000 in annual operating costs for these types of hypolimnetic oxygenators. Go ahead, Barry.
Yeah, I've been talking to Spanaway Lake, and Pierce County is trying to develop this for Spanaway Lake, but they're only talking about putting one of these systems in one portion of the lake, which really would not be effective for most of the lake. In our lake, for instance, with a 2-basin system with 2 deep areas, we would require 2 of these stations in order for it to even become close to being effective, wouldn't we?
That's correct. And so Spanaway Lake is a much smaller lake than Lake Lawrence. And so by having that lower system that is targeting the deep areas of the lake in order to sequester that phosphorus through oxygenation, that's expected to be effective. In Lake Lawrence, you would need to have likely one in both basins and potentially 2 to 3 even in the bigger basin just because of its size.
Right.
At this stage, I've not reached out to the manufacturers of these auctionators. Before I do that, I wanted to sort of gauge complete interest before starting to engage with like Paul Ganser and others in order to develop that. They would request additional information of that design that's sort of wrapped into this cost estimate.
Right, because one of the things that is required is you have to have land to put the system on.
Exactly.
You have to have power to that location, and you have issues with fishing, with anchors from boats and all kinds of stuff. So I just don't know how they get around that.
Yeah, and so in the Spanaway example, they have the benefit of a large regional park nearby where they're able to site the onshore facility where we have the oxygen generators, and then the Paul Ganser, who has designed OSTs, has spoken to like these are heavy things, and they would be more concerned around the anchor than he would his OSTs, but that may be a bit of hyperbole. I think that is certainly a concern, and I think flagging and communication around that, no anchor zone, would be my recommendation. I haven't checked in. I have some folks that I work with who are helping to support that design, and so I need to check in with them to see how they're handling that issue.
Yeah, I just at the estimates I heard from Spanaway are 2.4 million, but you probably have better data than I do. I'm getting it from the committee, not from the county. But again, we're looking at, to be effective in our lake, at least 2 systems, if not 3 to 4.
Correct.
Okay.
And so, as this is a very preliminary cost estimate, and so it is, I would say I should have put 1.8 million. That provides too much assumption of certainty. I would say in the millions of dollars. Between 1 and 10 million would probably be more accurate.
Okay.
I think the operating cost is probably about right, in the dozen or so thousand to 2 dozen or so thousand. So again, high upfront investment, but long-term benefit with meaningful operating costs here. So moving on. Oh, I had more information here, but I think I want to keep plugging away in the interest of time. The other option that we think would be feasible is chemical phosphorus activation of the sediments. This is able to remove phosphorus available for algae in the water column. Some of these are able to pull it from the water column, but then also to sequester what's available in the sediments, such that they provide stronger bonds to the phosphorus in the sediments than the iron. And as that organic matter decays, it doesn't dissolve upwards. It instead is bound to these. There are several chemicals available: alum, lanthanum, iron, calcium. And there's other proprietary blends like Utrasorb, WC, and Metafloc, which are not approved within the aquatic plant and algae management permit for the Department of Ecology, but there are experimental options available to get a waiver from that, and that's something that has been done for Utrasorb WC in Lacamas Lake in Clark County by Camas, Washington.
Mm-hmm.
So kind of speaking to this again is that we have this free available phosphorus that's in the water column as well as in the sediments, and then activation. Some of these are able to bind to that phosphorus that's in the water column and pull it down, and then sequester it and bind it in the sediments. I want to talk through each of these. There's a lot of information. I want to talk through alum, lanthanum, iron, and calcium. I'm not going to speak to the proprietary blends at this time. They have less information around them, and they also are
We
of
have a
higher
question.
cost. Oh yeah, go ahead, Frank.
You probably covered here, but my question was going to be, once, let's say, alum sequesters the phosphorus, is that a permanent sequestration? In other words, is that a chemical bond that will not ever break and release the phosphorus again?
Yeah, and so I certainly can't promise that it would never break, but those bonds are stable at certain ranges of pH. I'm going to speak to that here for each of these,
Okay.
how effective they will be. Frequently with alum treatments, as well as other sequestration treatments, the longevity of that treatment is going to be determined by the external sources of phosphorus and whether those build up, right, and start to overwhelm what's present, or whether or not that dose was enough to sequester everything that was in those lake sediments. So alum is available from general chemical suppliers in the region. It's able to form stable complexes with dissolved phosphorus. Also, when it's added to the lake, it forms floccules that are able to pull out particulate phosphorus as well. So it doesn't just take up that dissolved phosphorus, it's also going to add clarity to the lake by pulling out, as those floccules drift down, they're pulling out algae and other sediment. So after an alum treatment, lakes become very clear, at least temporarily, because there still is going to be some amount of nutrients and some amount of algae growth after a treatment, but immediately afterwards, it is very clear because it's all been removed. And alum is something that is typically used at drinking water plants and wastewater treatment plants for providing that clarification of water. And that is what is used in lakes, is the same stuff that is used for drinking water treatment. We use the same grade. For the ratio of how much kilograms of product is applied per kilogram of phosphorus to be treated, the range is between 2 and 20 kilograms aluminum to phosphorus. This varies depending on the goals. There are some lakes that look to do annual or more frequent alum treatments at a lower dose because it's more affordable and it provides that clarity and removes that phosphorus that's available at the time. So that is an effective tool that requires frequent annual treatment. Then there are larger efforts for sediment sequestration that are looking at a bigger dose to target all of the phosphorus in the sediments. And that typically ends up being more at a 20 to 1 dose. So when alum is added to water, it can cause a large decrease in the pH, because what it's doing is it's grabbing hydroxides from the water itself, because water is hydrogen hydroxide. And so when aluminum comes in, it grabs that hydroxide, and then we're left with just the hydrogen ion, and that is an acid. And so pH can drop a lot. And so alum has been known for causing fish kills due to that drop of pH. So at higher doses, it's standard practice to use a buffer of sodium aluminate, which is also alum or also contains aluminum, provides that sequestration. So, but it also controls for those shifts in pH to prevent fish kills.
So is that the difference between unbuffered and buffered?
Yes. So if we were to do an unbuffered small dose for Lake Lawrence, you would want to have a much smaller dose. This would be sort of an annual stripping type of dose, and they would only be looking at 6,800 kilograms. Whereas doing a buffered dose, which would include that aluminate, and looking more at a sediment inactivation, or what applicators call a lake reset, is nearly 10 times more aluminum. And so we'd really want to make sure that the pH stays stable. Right. This is something that has been recently done in Blackman's Lake in the city of Snohomish up north. Been working with them and they did a buffered alum treatment.
Yeah. It's similar to what Black Lake did 5 years ago.
So as I spoke to, there is possible toxicity with improper application to the swings in pH.
Mm-hmm.
And that has been observed in some Western Washington lakes. And so it's really important to have this planned out well and to do jar testing or bucket testing with the planned alum dose and local lake water to make sure there won't be those pH swings, and to have active monitoring done. And these are things that we put into our bid and contract agreements with applicators, is to make sure those outcomes don't occur. Permitting, this is included in the ecology permit under the aquatic plant and algae management permit. So for Lake Lawrence, I expect there's an existing aquatic plant and algae management permit for aquatic plants. A lake or a specific geographic area within a lake can only have one permit and one sponsor. So for application of this, either the person who currently holds that permit would need to be the applicator, or they would need to applicate that sponsorship for treatment in that area.
Yeah.
That's true for all of these chemicals.
Our county holds the permit for all 4 LMDs in the county.
Okay, great. That would expedite that process, but also require that the county is on board with the approach.
Right.
What I've provided here are some preliminary treatment costs based off of the amount of phosphorus within the sediment and within the lake water column for alum. Here, the low dose, that unbuffered dose, would be $90,000. The larger dose, estimated at $1.2 million. I know I said there's about 10 times more for the alum, but also this require for the buffered dose. But sodium aluminate also costs more than the aluminum sulfate, so that's why we have not necessarily a 10-to-1 cost, but costs more for that buffered dose.
Now, Clark, as I understand it, this can be a cumulative impact. In other words, if you do a low dose this year and a low dose next year, it's a cumulative impact on mitigating the sediment algae.
So that this is a sort of more novel strategy, and that is being applied in Lake Stevens, where they are, rather than doing these larger doses, they have cut it to be about, I think, is about 10% of the dose, and they're doing it each year, and so that eventually they'll sequester all that sediment. So they're doing enough to pull out what's in the water column, but then a little more sequester what's in the sediment. So initially you might think that the longevity is a year, but at some point it might end up reaching that same potential as a long-term treatment. This is novel, and so we'll be looking forward to seeing results for the Snohomish County effort as it's implemented. But I'm presenting it here. For this purpose, I'm assuming that the longevity is only a year for bringing out this long-term estimate, but there is certainly potential for just after 10 years of the unbuffered treatment that we might reach that same longevity than the buffered treatment. So with the buffered treatment, this again is really contingent on external sources, and what we saw, at least for 2025, is there's not that much external sources. Certainly during higher flow years, we might be seeing more that's coming in from surface flow and groundwater flow. But really, we saw about 90% of the phosphorus coming from the sediments. So by targeting and reducing that release rate, we expect to have a good amount of longevity of these treatments in reducing sediment release. Again, this is targeting 186 kilograms. Again, there's still those macrophytes, so there's still those other sources within the lake, still waterfowl,
right,
that will replenish it, and that's why we say 5 to 10 years. But there have been I think Lake Campbell was about 12 years in longevity. That depends on what you decide is the end of it and what is the critical chlorophyll A content.
Right.
So using those longevity in those annual treatments, I'm kind of did the midpoint here, would be about 2.8 million for an unbuffered treatment over 20 years, and a buffered treatment at 3.3 million. This includes monitoring costs, and so something that should be included when thinking about the unbuffered treatment is that each year that is done, monitoring has to be done, which is with the latest draft of the aquatic plant and algae management permit getting more intensive, including pre and post monitoring for I think 9 months now, looking at total aluminum in the water column, sulfate, pH samples, and a few and dissolved organic carbon, hardness, and so those all cost money to do. You have to send someone out to do that sampling at different stages. Sometimes that could be in partnership with the Thurston County Environmental Health, but it does cost money.
So are these sediment core samples, or are these water?
These are water samples.
So the same thing that the county is doing now between April and October.
Not, but with additional parameters.
Okay.
That would be probably an extra $100 to $200, and then additional analysis and reporting to the Department of Ecology. So what I've estimated here is about $50,000 of additional for monitoring per treatment that's done.
Per treatment.
Per treatment. So that adds into that 90,000 for the. Sorry, that includes makes that 90,000 a little less cheap, but still. And I haven't costed it out fully. This is an assumption of $50,000. It might be a little bit less, and so as I move forward in the plan, that amount may go down. It's about what I would expect, but that these numbers will get refined as we have interest in there. But it's a good ballpark, especially if you're comparing across these different chemicals. Go ahead, Frank.
The toxicity that is specified here, is that plant and animals or humans or both?
That's a good question. And so we're thinking of just aquatic organisms here, and really fish and trout are the most sensitive to these swings in pH or to aluminum toxicity itself. As we have lower pH as well, that aluminum doesn't bind to the phosphorus, and so we really don't want that either. It doesn't form those stable complexes, and so that's why that buffer is necessary. But really, we're thinking about aquatic organisms. The concentrations we're talking about for aluminum here are not a concern for human consumption.
Okay, so that's
exposure.
That would be a positive statement that it is not toxic to humans.
Right. Yes. Alum is used in pickles. You probably have it on the shelf.
Yeah, I wasn't thinking about just the alum, but the resultant chemically bound phosphorus.
Yeah.
And there's no adverse human effects there. We'd have to shut the lake down, anything to that effect. I mean, that's really important on our lake.
Mm-hmm. Yeah, for all of these chemicals that I'm laying out, there's no concern for human toxicity at the prescribed.
I think that we should probably put that on there,
Yeah.
to specify that there is no human toxicity. The toxicity that's being used here is plant or wildlife.
Mm-hmm. Thank you. That's a good clarification. So I see there's a couple more questions. I want to get through all of these, and then we can probably discuss them all at once. And then I know that we have about 15 minutes left here. I have a few more to talk through, so I'm going to few more options to talk through. So let me go ahead and get through this slide and the next few, and then we can have a larger discussion. So lanthanum is available as Phoslock or Ugisorb G. It also forms stable complexes with dissolved phosphorus. It doesn't form those same floccules, so it doesn't pull out particulate phosphorus. It has a different binding ratio of 5 lanthanum to 1 phosphorus. So it wouldn't be useful as a stripping dose. You still could do annual dosage of this to decrease the overall upfront cost, but it wouldn't have the water quality benefit that you would get from alum treatments. For a sediment inactivation dose, I would be looking at 16,500 kilograms lanthanum. The two products have different concentrations of lanthanum, so that would be 165,000 kilograms of Ugisorb G or 331,000 kilograms of Phoslock. There have been some studies for aquatic life toxicity for lanthanum in lake and sediments, but not expected at the dose. What is applied as lanthanum is bound to clay and then binds to phosphorus. The toxicity they're concerned around is free lanthanum, sort of lanthanum ions that are in the water, but because there is this bind to clay where it settles to the bottom, then it forms the balance with phosphorus. So we wouldn't expect to see free lanthanum in the water. The newest APAM treatment, the APAM is the Aquatic Plant and Algae Management Permit, is going to require lanthanum monitoring, so we're going to actually get some data on that free lanthanum that's in the water column. So I'll be looking forward to that information. The treatment cost, an individual treatment cost, is $1.8 million, expected to last between 1 to 10 years. So for a 20-year treatment, assuming a 7.5-year longevity and that $50,000 for monitoring per treatment, would be about 4.9 million. So a little bit more than the alum. Iron is available as zero-valent iron and iron salts. Iron hydroxides and oxyhydroxides provide binding sites for phosphate and other ions. However, iron phosphate bonds may break down in lower oxygen conditions. There's been some recent studies showing that zero-valent iron may be effective at lower oxygen conditions, but not. This is a growing body of literature, and so right now we don't have utmost confidence in that. And I know that there's a few lakes, like Steilacoom has been using zero-valent iron, but they've been using that annually and really targeting that as a water stripping device because there's not because the sediments in Lake Steilacoom is not the major source. They've been using zero-valent iron as a stripping dose. The mass dosages for iron vary. The last I heard or got quoted was 44 to 1. So using that would be about 150,000 kilograms of iron. We wouldn't expect major negative consequences with the use of iron here. The current ecology permit allows use of iron, but does not allow it in potentially anoxic areas. I know that there's been some advocacy for allowing it, but at least it could have experimental use permits in the anoxic areas of Lake Lawrence. Additionally, as I spoke to with the oxygenation, if using a hypolaminetic oxygenation system, some supplementation with iron may be needed. At that point, the deep waters of Lake Lawrence would have oxygen, so this permit condition would not hold. Iron is a lot cheaper than the other chemicals. So at a single dose here would be $270,000. However, there's a lot of uncertainty for longevity. potentially only lasting 1 to 2 years because we do have uncertainty on whether it will hold that bind with phosphorus at low oxygen conditions. So it may end up costing $4.3 million. However, that is an upper bound. It could be much less if we find that zero vinyl ion is effective at lower oxygen levels. So this would be kind of stress the importance of monitoring and looking to see, is it working before continuing to just treat 20 years blind. So it's great that Thurston County Environmental Health is already continuing to do that monitoring, which is great for managing that effectiveness. Finally, this is something that Barry shared with me, was the CDOX, which is a calcium containing a proprietary blend from OASE manufacturer. Calcium, when it's added to the water, forms calcite or calcium carbonate, which provides stripping of phosphorus from the water column and may sequester it in the sediments. However, it's less effective at lower pHs, and the pH in Lake Lawrence is typically between 7 and 8, sometimes higher during algae blooms, but we wouldn't necessarily expect that calcium would be able to hold its bond with phosphorus in Lake Lawrence, especially in the deeper waters. I imagine that OASE has a response to that, and I'm skeptical of it, but I would be interested in hearing what you heard, Barry. Their recommended dose is 50 to 1 of CDOX, 1 kilogram to 1, so that'd be 165,000 kilograms. Based off the pricing I saw, this would end up looking at $2.7 million per dose, and with an expected longevity of less than 3 to 5 years. This is again thinking about that dose breaking down at lower pHs. Even not low, this is neutral pHs. Calcium is really effective in like hard water lakes, so it's used often in northeastern lakes. Would be 13.8 million over a 20-year period. However, could be less if it's found to be effective, or if OASE has found a method to get around this pH issue. But it is a nature of the chemical bond of calcium carbonate that it's not stable at lower pHs.
Yeah.
So
just
yeah, go ahead.
yeah, I had a 45-minute conversation with him today. I've got I took mostly a video of most of it, all but about the 10 minutes at the beginning. I'm going to send that to you after this. I'm going to send it to the people that were on this call too, so they know. Actually, it's CDOX Max that we would be looking at using. Okay. It is more effective than CDOX with the pH levels below 9. It also provides oxygenation at the lower depths, which none of the others do. It is not approved in ecology permit right now, as you've indicated there. It would require a plan to be developed and approved by ecology.
I think CDOX would be, because it's calcium carbonate, but the max.
CDOX Max is calcium chloride.
Calcium peroxide.
Calcium peroxide, right?
Okay.
So, you know, we'll take a look at it. The cost estimate that you have there, according to them, is about double what they're estimating it to be.
For the treatment or the long-term cost?
For the treatment and long-term costs.
Okay.
That's something that I'm going to send you their information, a copy of the video that I took, and the point of contact, the vice president for global sales, and the technician and sales manager for UASA.
Okay.
So that you can get more detailed information from them to include in this study plan, to give us a little bit better idea of what we're looking at. The thing I liked about the product was the fact that it does both. It strips the water column, it sequesters the phosphorus. It releases oxygen into the water, which the other products don't do. Lanthanum and iron, as you mentioned, don't strip the water column. Alum does not produce oxygen. Calcium, Cedox Max does both. So we're going to take a hard look at it.
Sure.
But
I'd be interested in the longevity of that oxygen release from a peroxide. I mean, you know, there are other peroxides that are added to waters as part of algicide, and
right,
it's very short-lived how long that oxygen is in the water. So it could be a flash, and then it's
the other thing, Clark, is we're looking at Utrosorb G or Utrosorb SI.
SI, yeah.
Not Foslock. I've got a lot of information on ZVI as well. I'm not convinced from the information that I have that it's not a reliable way of doing it. I think it is a reliable way of doing it, particularly for our lake, because our ratio of Fe to phosphorus is very low in our lake, as you pointed out in your study, particularly in most of the area. But again, I'd like to hear from some of the other folks on this, and then we'll have more conversations about this next month. I've also got Utrosorb, Utrofix, going to give us a presentation to our steering committee third or fourth week of January. I don't know at this time if I'll ask UASA to come and do that on CDOX Max or not. But I'm also looking at potentially someone from Hoganis to give us a presentation on ZVI. I've contacted the company and talked to Pat, who is their technical expert there about ZVI, and we'll go here. But these are the products that we're looking at right now. I do not believe the oxygenation system for our lake is financially doable for us, based on our budget. We're only looking at about $100,000 to $105,000 a year, or about $200,000 every other year for this type of sequestration. So I don't know if alum or calcium or Utrosorb would be effective for us. I know that Long Lake does Utrosorb twice a year.
Right.
They do it fall, and they do it low dose, fall and spring, which I don't know how that works into your calculations here of 5 lanthanum for 1 P at 16,500 kilograms of lanthanum.
So I'm looking specifically at what's in the sediments.
Okay, so you're looking at a total sequestration.
Total sequestration. I think Long Lake has, I think, a higher amount of external loading, so they're looking to sequester what's coming in as well.
Correct.
Year after year, whereas Lawrence has the benefit of low other inputs. It's really primarily the sediments, and so each of these methods should have increased longevity because of that, because there's not new phosphorus that's coming in. So a dose that's being put in would match the phosphorus levels in the lake, at least for 4 to 8 years.
Right.
I think Utrosorb SI is a very interesting chemical as well. It's also, I think that's bound to iron, and I think that's being added to the next aquatic plant and algae management permit. So this would allow the sort of addition of iron as well, which would work well under oxygenated conditions.
Right.
But then when there is low oxygen, then that lanthanum is released, and so it's a pretty exciting addition to the toolkit, and one I'll need to get added to here soon. I want to say we're at 8:29. I got a few more to get through. for these preliminary cost estimates to make sure to try to get everyone onto the same page. And I do want to have a little time for discussion, so we are going to go late because we're 8:30 now, so now we're going to go late. So
Go ahead. I've got about 19% left on my battery, so I may stop you and replace my battery. Okay.
I work well under pressure.
Okay, go ahead.
Battery pressure. So there was a lot of interest in dredging. There's two methods there. There's mechanical and hydraulic. Mechanical is using a crane, a boat, and a barge in order to scoop up sediments and then bring it to shore. Hydraulic dredging uses an underwater cutter and pumps to create a slurry and then pump that up and out, being a floating pipeline. Sediments are dewatered on the shoreline. They can be hauled away or disposed nearby. Oftentimes, that hauling away is some of the higher costs associated with dredging. From past work that was done in Lake Lawrence, there's estimated need to be 4 to 10 million cubic yards would need to be removed. To kind of put that in a sense, that's enough area to cover 100 acres with 25 to 60 feet of sediment, which is a lot of sediment. Dredging requires a lot of permits, federal and state level and local from the county. U.S. Army Corps of Engineers, going through SEPA, hydraulic project approval, shoreline development, aquatic use, and then estimates from the 1995 dredging feasibility study thought that dredging of the lake in its entirety would take more than 10 years. That might be faster using a hydraulic dredge, but additional information would be needed talking to them. But I've talked to some folks. We reached out to Sea and Shore Construction to get an estimate for different dredging costs. They estimate it'd be $55 to $75 per yard plus mobilization and the trucking costs. So this is these costs I'm presenting are not the total cost either. Additionally, due to those permits, the amount of extension, I talked with some of our permitting folks here, and they expected that permitting and planning to be around $200,000 before the work even starts. The near-shore dredging, which was a preferred option coming out of the 1995 plan, due to the high costs of dredging the entire lake. This would be to really improve recreation and homeowner access to the lake. So it wouldn't necessarily improve water quality. That would cost $7 million if the materials to be left on site, $9 million if hauled away. To achieve that water quality benefit and remove 4.6 million cubic yards. The cost ranges are $250 to $343 million. And for the entirety of the lake, we're looking at 579 to 790 million. These are early estimates from them, but this does provide a ballpark of an order for to have water quality benefit through dredging. We're looking at costs on the order of hundreds of millions to potentially $1 billion within the lake. And the 1995 nearshore only estimate from 1995, again, they estimate 1.85 million, which included hauling away. If we were to put that into $2025, that's $3.9 million. So we're in the same ballpark here, but it seems that there may have been additional inflation and costs of management compared to 1995. So we're looking at really high amounts here.
Okay, I'm gonna try to help you speed up this. If you can go ahead and go through these, we can see the numbers and everything. So these are not really effective measures, but go ahead.
Yes, so algicides provide a rapid and effective way of removing algae in the column when it's there. It kills all sorts of algae. and sometimes can kill fecal bacteria. They don't reduce the nutrients. They don't provide long-term control. Peroxide-based ones do break down into water and oxygen, so there's no chemical residual. There are other types of algicides like copper sulfates, but those are not allowed in the state of Washington. Immediately after treatment, those can increase the nutrients. Still requires a permit. This would require frequently, if there's an algae bloom, an algicide can only be done to a quarter of the lake. Otherwise, there would be high amounts of oxygen demand from the rotting algae. So it doesn't necessarily treat the entirety of the lake, but it can be effective in like enclosed areas. And we've done some look at feasibility of generating kind of a management zones where we put in a boom or a sediment curtain to protect the swimming beach area, and those algicides can be focused in that area. So it's a smaller area to manage and can have cleaner water while the lake has a bloom elsewhere. So this is a short-term solution that can really work in small areas that are isolated from larger blooms, which would be challenging in Lake Lawrence. Mixing circulation, we don't have a lot of confidence in them being used. This is really looking to combat algae blooms by mixing the water, preventing that dominance.
Yeah, this is not something we're going to do, Clark. So
great. If there's agreement with that, I just want to make sure everyone's on the same page. We wouldn't recommend it, but I want to provide this information to folks. Aquatic plant harvesting. This is some work that's already been done, but in select areas. I'm not going to go through this process, but it is removing the bound phosphorus that's in there. We have an unknown amount of phosphorus reservoir within the aquatic plants, so we were able to harvest it and remove it. That can at least reduce some of that release in later during senescence.
Yeah.
This would require ongoing management and cost thousands of dollars per acre.
Yeah, we've done this a couple times. We've got a video on our website all about it to tell people what we're going to be doing on this, but not a lot of plant harvesting.
Yeah, and it's expensive at a whole lake scale.
Yeah.
Algicide or herbicides are not going to be effective because they're just going to kill the plants there, and they're going to release the phosphorus as they decay. There's also experimental emerging technologies, which I would stay away from. They're not very well studied, and they have variable results. Sonication, ozone, nanobubbles, barley straw, shading. So those are all recommended. And there's a summary here. But we also want to look at watershed management controls. Groundwater is not a major source, but it is an important source to consider. So looking at maintaining existing OSS systems, making sure they're not failing, causing undue phosphorus loading to the lake. So staying on top of that, reducing fertilizer use or using phosphorus-free fertilizers, developing shorelines to not be friendly to waterfowl to help reduce their presence and loading. There's not a lot of agricultural in the watershed, but the limited amount of like hobby farms of just managing manure from livestock can really be helpful.
Okay, I'm going to stop it right.
Okay, I had two questions. One of them is this lake in the summertime gets to be very heavily boated with boats going around, and it starts with a big outboard regatta and ends with an inboard regatta with lots of boats really churning up the water. And don't get me wrong, I'm not against them. These are just what's happening, and lots of people out there with boats. How's that going to affect our treatment where we're having the phosphorus drop down to the bottom of the lake?
That's a good question. So as this turbulence is happening, we're going to have that. So for the primary dose of, like, if we're looking at a sediment inactivation treatment with alum, lanthanum, iron, calcium, we're really targeting those deeper waters, and so the turbulence from those motors are going to be less impactful, though certainly there is some amount of mixing that does occur due to turbulence. However, because of these stable bonds, they will get mixed up, but they're going to stay, that phosphorus is going to stay bound to aluminum or lanthanum, and then resettle down. So we wouldn't expect it to become bioavailable. Additionally, and I didn't show this, but a lot of the available phosphorus in the sediments is at the surface, because that's where it tends to migrate upwards within sediments. And so really we're looking to capture that surface level sediments. And so the turbulence, is not going to mix up at the bottom of the lake down to 5 or more centimeters. And so we're looking to inactivate that top 10 centimeters. And that's how we're basing our dosage. And so we wouldn't expect that amount at those depths. Certainly that would be impacted in more shallow areas, but those aren't the targets of these treatments, because really the sediment release that we're expecting and is going to be associated with those deeper sediments.
Okay, and the second one is just a request. Can we get maybe a chart of the treatments and the costs, short term and long term?
Yes, and so that's something that will be developed as part of the management plan that we're putting together. What's in here is sort of these preliminary estimates, and I've shared this with Barry, and he's able to share it with you all. But I would, caution with, taking everything as truth. This is all preliminary estimates for costs. I haven't gone out to each of these vendors specifically to ask what their estimated dose and the most up-to-date cost of their product is. So these all are going to be subject to change, but these are good reference for relative magnitude of cost.
Yeah, John, this entire presentation is on our website right now,
Okay.
on item 2 of the homepage.
Okay, yeah, we're going to be getting requests about this from people,
Right.
other voters that we want to bring into the program. So anyway, thank you.
Thanks, John. Stephen?
Yeah, I'm based on what you've shared tonight, I've become less excited about any of these chemicals being used. The toxicity for the fish brought to the question of, well, it's not toxic for me, but the fish is. And well, how many fish do I eat before it becomes a problem for me? Because if it's bad for them. So
with these, they are not chemicals that bioaccumulate in fish. They don't really stay in their tissues, and the concern around toxicity to fish with aluminum specifically, or alum treatments, is that change in pH and toxicity that occurs to their gills. So it's not necessarily it's not necessarily a ingested toxicity, and so we wouldn't expect, from years of and decades of research in alum treatments, there's not been effects on human endpoints. So I would caution you from that conclusion or speculation, and I'm happy to provide additional information there.
I look forward to that because I'm really kind of more excited about the idea of the oxygenation and the dredging, and maybe we just need to find some other companies for those kind of services. Thanks.
Well, we've looked at 3 different companies, Steve, and you're looking at $350 million plus, regardless of which one you go with. So, and those are studies that we've done since 2004. We've had 3 different estimates. This is the latest one. They all are above $350 million.
keep this alive, especially in front of the government, we had 2 sawmills on the lake. And Barry, correct me if I'm wrong, but I know one of them was near me, Law 2, LEW2.
Correct.
On your chart 15. I think the other one was SS3 is actually over by John Carpenter's house.
Correct.
SS3 is your designation, I guess. Anyway, I don't know the aspect of phosphorus, but that's certainly a lot of organic material that was added to the lake. It was human caused. It was government approved, just like bringing the Deschutes River into the lake. And we didn't talk about them, and I'm not sure we need to spend a lot of time on them. But the fact of the matter is, they have probably produced a lot of organic mass that's still in the lake. I mean, I'm still pulling logs out of the lake that were likely at the sawmill near me. I mean, they're buried in a lake. So I don't know if organic mass, meaning wood, would contribute to any of this at all, but if it does, particularly the sediment that's in the lake, the west shore where Law 2 is, and probably to some extent over by John there, that organic mass is probably somewhat of a result of all that wood that's just kind of buried underneath in the sediment.
Yeah, thanks, Frank. And
my point there is just I would bring that out when you show slide 15 that shows all these different sites. That was Law 2 and SS3 were the sites of sawmills that were, again, a government decision to allow us to do that, put them on the lake. I don't know, Barry, you got any comment on that? Or
Yeah,
John?
there was no government decision. Those were back in the late 1800s to the really early 1900s. Those were property owners that just built sawmills of anywhere between 3 and 5 people and kept the logs in the lake and brought them out to saw them up, and all the debris got pushed into the lake. And then when we made the reservoir in 1908 to 1928, that all flooded, and all that debris that was on the land from the sawmills got pushed into the lake by the water and rising water. And that was approved by the government. It was a taking of the land for 20 years by the state.
And I would suspect, and I have not seen data specific to sawmills and sawmill waste for phosphorus content in lakes. I think that's likely has existed. Many of our lakes out here have had sawmills, not all of them. But that's a uncertain question. I think within Lake Lawrence, my expectation would be that the primary source was going to be through this Deschutes diversion due to the high amount of logging that was happening at the time. There's just going to be a lot of sediments that were deposited from that, as well as from agriculture that was occurring in the lowlands. So there's just that I expect would have been the major source here, and that the sawmill was a sprinkling on top of it. Would it be my expectation? Again, that's not something that we are able to determine through our study at this time of pinpointing the source of it, and it's not really something that's readily done through phosphorus. It's not really a concerted tracer like that. But I think that is important information, and I think I would like to make sure we include that within our history section. Go ahead, Terry. And you're muted.
Sorry,
Yeah.
yeah, I had to unmute.
No worries.
This is kind of in just a comment. I think it was Stephen that mentioned oxidization. Last weekend we were talking with my sister-in-law, and they used to live on Stillicum Lake, and she said they did oxidization, but they did not put enough machines out there, whatever you want to call them. And I think you mentioned that the big lake here would need maybe 3 or 4, so the cost is going to go up. But she said when they did it, it didn't do anything. It didn't help them enough. So if I was just kind of make the comment that if we were looking at that more, we'd really need to make sure we put enough in that it would do good. And now you're talking way unaffordable from what I saw on your chart. But that's just a comment because she said it didn't work there, but they only had, I think she said they had one, maybe two on their lake, but they've got a smaller lake, I think.
Yeah, I'm not certain on what technology Lake Steilacoom used, if those were solar bees or something like on a smaller scale.
They were.
I can't
They were.
remember what she
Yeah.
said.
They
Yeah,
were.
I don't think she knew, but she just mentioned that it didn't work for them, and it was costly at the time, and so that was something that if we were going to look into it more, I'd really want to know more about it and exactly how many we'd really need to do any work. But like I said, from what I saw in your chart, it would be so costly that.
If I'm recalling, I think Lake Steilacoom looked to put in 9 solar bees, and 9, those are not oxygenators, they are just circulators, and so they're just looking to move water around, and so they are just sort of pumping water. And again, those are things I don't have a lot of confidence in.
Okay, and that may have been, she couldn't remember.
Slick salesmen, and it seems like a great solution because it's set and forget it. But there has been multiple lakes in which these have been installed and then pulled from due to a lack of success. I would love for them to be successful. It's a very cute name.
Not living on the lake anymore. She just happened to mention it because we talk about this lake. So yes, they all grew up here. Thank you.
Kim?
Hey, so I'm on a learning curve here with all this. We're still fairly new to this area. But I remember, and this goes to the history that we're talking about and the kind of the diversion of the river. But somebody had mentioned in the very first meeting that Puget Sound Energy was a big part of coming in and doing a lot of stuff to this lake. And I don't know if that ties into you're putting up history?
Yeah, here's some history. I have this in the back.
So is Puget Sound Energy in there somewhere? Because I thought that was really interesting.
It wasn't PSE. It was Olympia Power and Light Company in 1908 to 1928. And PSE bought them out and then closed down the reservoir.
Gotcha.
And the power plant at Tumwater Falls in about 1927, 28.
Because, I just thought when we're going after funds and stuff, that might be an organization that might have tied into what happened to our lake, and maybe that might be worth looking into.
There's been a lot of discussion about lawsuits with PSE who bought out Olympia Power and Light. It's just, we just don't need to go there, quite frankly.
Gotcha. Okay, thanks.
Yeah.
Any other additional thoughts or questions on the management options I presented?
Hey, Earl, you had a comment in the chat about dredging. Do you want to make a comment?
I don't know enough. I'm just saying that, if that's the main source of the problem, if we could slow boat this the way it was slow Ickard, yes, I understand it's extremely expensive and whatever, but if we're talking it took 30 years to get here, how about 30 years back? And just incorporate that into some sort of long-term solution rather than just chemical. That's just a thought.
Yeah. Just for your information, we did an actual dredging study for Lake Lawrence. We actually put a dredge at the public boat launch, and we sucked sediment out to try to determine how well it would work as far as siphoning the silt out of the lake and putting the water back in the lake, which is going to be required in any dredge.
Right.
And the cost was just absolutely insurmountable, as well as the time period in conducting that operation. As Clark said, initial estimates for us were 10 years. That has been extended to more than 10, maybe 10 to 20 years to do that with lake closures, etc. and cost of 350 million plus. For our size lake, it just is impractical. I mean, we even talked to local farmers and ranchers about utilizing their land to put the sediment on, but as Clark pointed out, 100 acres for dredging the amount of sediment we would need to remove from the lake would be 20 to 25 foot deep over a 100 acre area. It's just not going to happen.
Well, and I'm new to this, so I appreciate your patience.
Yeah.
I just think that some physical reformation should be at least considered in any chemical reformation.
Yeah.
I come from a long background of inspections, chemicals, all that type of stuff as well.
Yeah.
And just something that I'm new to this. It hasn't been considered great. Could it be over the long term of a longer term plan rather than immediate? I don't know. I'm looking at what the 1 year guarantee, maybe 5, maybe 10, or millions of dollars, and then there's really no guarantee. We're also dealing with just surface water contamination, not the whole breadth of the water depth, right? So we're not talking about fish. We're not talking about wildlife. We're just talking about the algae bloom that's on the surface. I understand sand and phosphorus come to the surface, but we're only looking at one aspect. So my question is, because I'm new, are we looking at all of the things and any remedy? And nothing's going to be cheap, and nothing's going to come quick.
Yeah, that's why we're doing this, is to look at all the different remedies. I would prefer oxygenation systems.
Love that.
But it's just, I mean, I could go into an hour dissertation about what it would take to put that type of system together, as I'm sure Clark could, give us a lot more information. But I have personally talked with the Spanaway folks, the Pierce County folks that are trying to do that in Spanaway Lake. It is a monumental task. It is very expensive. And for our lake in particular, as Clark and I have both pointed out, would require multiple systems, which means multiple properties that we would, as a lake management district, have to purchase or get lease agreements from those property owners to put these systems up. Because we don't have a city or county park like Spanaway Lake does where they can put this system up there. And you got to have power to it.
First of all, I so admire that you have taken this upon yourself. I'm new to the system. I just want to be a benefit to it.
Yeah.
And I would offer the dissertation after this meeting, for sure. Because I think that the term solution is long. It's long gotten, right? And we care about the lake. We don't want it to die.
Right.
We want it to. So what is the best that suits all around all the concerns? The fish, the wildlife, the everything else, right? Not just the surface.
Yeah.
What can be that? None of it's going to be cheap. We do it. So anyway,
that's what we're trying to do, is come up with the best solution for our lake. Gather as much information as we can and make the best decision.
Yes, sir.
And it's going to be a difficult pull.
It'll be a long, expensive haul.
Right.
For sure. We all know that.
Yeah.
Well, thank you.
Yeah. What other comments do we have, folks? I don't see any other hands up.
Thank you.
Oh, yeah. Thank you, Earl. Appreciate it.
We'll talk soon.
Okay, Clark.
All right. Well, thank you all. We appreciate all the questions throughout the discussion at the end here. I think this is really critical. This is what we're trying to gather on. I don't want to show up at the end of this and just have a plan that you have no idea where it came from. So hearing the concerns around human toxicity, hearing interest in these long-term solutions and not throwing everything out, but then also knowing that there's not a lot of interest in experimental. You want something that should work and is expected to work, is really helpful to help guide what we're doing next in the plan. So now we're going to be going back in, finishing out our data analysis, putting in that additional data from Thurston County to then develop this plan based off of what we've heard today. I plan on reaching out to Paul Ganser with the mixed hypolytic oxygenators to help get a cost estimate for Lake Lawrence. We'll be reaching out to OASE and talking to Nutrifix to help refine those cost estimates as well. So I want to thank you, and then you'll be seeing a pre-draft plan. At least the steering committee will in March, and then a draft plan for everyone in April, along with another one of these lovely presentations. I'm hoping I can come up for one of these and have this be in person. I really enjoyed being out there last time, and so I'd love to come out in April or June next year. With that, I really want to again thank you all for your time and wish you all a good night.
Clark, I got one final question for you.
Yeah, go ahead.
Does our lake have about 70 parts per billion of phosphorus, total phosphorus? Is that about right? About 70?
It varies. As an average, I would say it's between 50 and 70 parts per billion. It's going to be vary on the year and the season. So I think for planning purposes, I guess what is the context you're asking in?
Well, for mitigation, how many pounds of product does it take to do that?
I think looking at for a water stripping, looking at 50 to 70 would be a good range. And
okay.
I think 70 would give you a good upper estimate for it. For my estimates, I've been using 50. That's more of a early season average, which is when we would be doing the dosage. It picks up over the course of the summer as the sediments release.
Okay. Steve, you got a question?
Well, just a comment that he'd asked earlier about the different bird populations. So, it's just nice to know that about 5 years ago we had over 200 geese regular on the lake, and we have taken action to reduce that over the past 5 years. So now I think the last time I went out with Barry, we only counted about 30 birds. So that's in the long range of everything on the lake. That's kind of a short-term development, and probably hasn't affected or shown much effect yet, other than on people's lawns. But as far as the water and everything that's been dumped into it for all this time, I know that kind of thing will take more time to resolve.
Right. Yeah. And so, and that's what is really critical. So, whether it is a removal of these sediments or a sequestration, the control of those external sources of waterfowl, of septic systems, right now they're a small piece of that pie, but as I showed, a lot of the phosphorus as enters the lake stays in the lake, and so it's going to build up in those sediments, and so eventually, maybe you'd be decades, maybe half a decade, maybe 2 decades, that those waterfowl feces and septic systems would replenish the reservoir such to reservoir of phosphorus in the lake bottom, such to cause algae blooms again. So controlling those in tandem with the sediment source control is going to be important for the overall longevity of the system, or you just end up doing consistent alum treatments or lanthanum treatments or dredging.
Yeah. So any plan we put together, Clark, is going to have to take into consideration that we only have about $100,000 a year to put toward this. Mm-hmm. So it's going to be metered out over a period of time. And one of the other big things that we're going to need to take a look at with your study is testing. What's the cost of that? How do we do it? Who's the best person to do it? That kind of thing. So
we will be incorporating that management and monitoring as part of this.
Right.
There is an incredible value to all of your time in taking this active management. Typically, I do like to include that as a cost. Right now, I think you're all acting as volunteers to support the lake, which is incredible. There is, the cost of the administration from Thurston County, but your work is indispensable. The implementation plan is going to take into account the current funds that the lake has. There are grants and loans that we will be exploring to fund this. The combined, the Clean Water Fund is a low interest grant that could be available for doing some of these big ticket items, whether it's oxygenation or larger alum treatment. Right now, several grants do not fund in lake management treatment.
Yeah.
And we're working, I'm working in a separate effort to change that, and I think we're making some pretty good progress. So I'm hopeful that there will be opening up beyond the current freshwater algae control grant, which is a useful but not enough $50,000 to getting to projects that could be up to $500,000, which is very meaningful, especially if accompanied with a grant or another loan. And so we can.
Right.
So I'm working on that, and so I'm hopeful I can.
Well, loans and
there.
bonds aren't the types of things that we're able to get. Just for your information, that's not something we're eligible for as a Thurston County Lake Management District. Loans, we're eligible for grants, but bonds and loans are not. We're not able to do that.
Is that specific to
Thurston?
Your charter?
Yeah.
Okay.
Specific to Thurston County. Yeah.
Okay.
Yeah.
I'll talk to Larry Schaffner's retiring. There's some other folks who might be willing to sponsor that outside of the environmental health group.
Okay. Terry?
So,
all I was going to say is I wanted to thank Tim for the presentation. It was informational. Isn't his first name Tim?
Yeah.
And then I want to thank Barry, as always. He's a lifesaver to our lake. I can't thank him enough for all he does. That's it.
Thank you. Okay.
Yeah. It's been a real pleasure working with Barry.
Okay. I just like to say that, I was pleasantly surprised by the number of people that we had today on this call. I've counted over 22 individual coming up on it. I really appreciate everybody's participation and look forward to that in meetings 4 and 5 coming up next year. And thanks again, Clark, for the presentation. I know it was long and difficult, and we're way over time, but I appreciate it.
Good things take time.
Yes, they do. Thank you very much, everybody.
You all have a great night.
Thank you.
Thanks. Have a great night.
Merry Christmas, everybody.
Merry Christmas. Take care, Steve. GoPro, stop recording.